Every year, the rains return, and every year, the beautiful city of Greater Accra holds its breath. What begins as a few hours of rainfall quickly transforms into a citywide emergency. Roads disappear beneath muddy waters. Businesses close their doors, and schools suspend classes. Emergency services races against time, and thousands of residents find themselves trapped in homes, offices, or vehicles. For many Ghanaians, this has become more than a seasonal inconvenience. It has become a cycle of disruption, a recurring paralysis that affects lives, livelihoods, and the economy. The devastating floods of June 2026 were not an isolated event. They were another reminder that despite years of drain desilting, emergency dredging, and seasonal cleanup campaigns, Accra remains dangerously vulnerable. The question is no longer whether the city can respond to flooding. The real question is whether the current strategy is still enough. Every rainy season, excavators remove silt from drains. The government organizes cleanup exercises. Authorities clear gutters and waterways. Yet, when the next major storm arrives, many of those same communities flood again. The question is why? Because dredging addresses the symptom, but not the system. Many drainage channels were designed decades ago for a much smaller city with lower levels of development and different rainfall patterns. Today, Accra's population has grown dramatically, and vast areas that once absorbed rainwater has been replaced by concrete, asphalt, and buildings. As a result, rainfall that once soaked naturally into the ground now rushes rapidly across hardened surfaces, overwhelming drainage networks that were never designed for such volumes. At the same time, more intense tropical storms, combined with blocked drains and development on natural waterways, have pushed many parts of the system beyond their physical limit. Accra now stands at a crossroad. Should the city continue relying primarily on reactive emergency measures after each flood? Or is it time to rethink flood management entirely? Around the world, cities facing similar challenges have embraced a new generation of engineering, combining underground infrastructure, smart technology, green spaces, and nature-based solutions to reduce flood risk before disaster strikes. This documentary explores those innovations, not simply to imagine what is possible, but to ask a critical question. Can Accra move beyond seasonal survival and build a future where flooding is no longer an annual crisis? Because the solution may not lie in clearing one more gutter. It may lie beneath our feet. Imagine if, instead of fighting floodwaters on the surface, Accra could quietly redirect them beneath the city, invisible to motorists, invisible to businesses, invisible to millions of residents. Welcome to what engineers call underground stormwater storage, an approach already used in cities such as Tokyo, Singapore, and Kuala to reduce the impact of extreme rainfall. Rather than allowing every drop of rain to rush directly into rivers and drains, enormous underground reservoirs temporarily store excess water until the storm has passed. For Accra, A similar concept could transform the way the city manages flood. Instead of relying on a single drainage channel, engineers could design a network of tiered underground storage reservoirs beneath parks, open spaces, or other suitable public land. During heavy rainfall, stormwater will be diverted into these chambers before it reaches vulnerable waterways, such as the popular Odo River. Each reservoir will temporarily hold vast quantities of water, reducing the volume entering the drainage system at the most critical moment. As river levels fall after the storm, the stored water could then be released gradually in a controlled manner. Instead of one overwhelming surge, the city would manage rainfall in carefully timed stages. Now imagine the drainage system as a highway. When traffic becomes too heavy, additional lanes help vehicles keep moving. The same principle can apply to stormwater. Engineers can construct modular bypass channels that operate like high-capacity express lanes for floodwater. When the main drains approach capacity, automated gates redirect excess flow into these secondary tunnels, carrying water safely around congested sections of the drainage network. Rather than forcing every liter through one overwhelmed channel, the water is distributed across multiple pathways designed specifically for big storm events. One of the greatest advantages of underground storage is timing. Flooding occurs because too much water arrives too quickly. By temporarily storing millions of liters beneath the city, these channels reduce pressure on drainage systems during the most intense hours of rainfall. Instead of overwhelming rivers and canals all at once, water is managed in a slower, more controlled way. The result is lower peak flood levels, reduced strain on infrastructure, and more time for emergency services to respond where necessary. No engineering solution can eliminate every flood, but modern cities increasingly recognize that resilience comes from combining multiple strategies. Underground storage, bypass tunnels, upgraded drainage, green infrastructure, and effective urban planning work best together. For Accra, the challenge is no longer simply removing water after the storm. It is designing a city that can safely manage extreme rainfall before disaster unfolds. Because sometimes the most powerful flood defense are the ones no one ever sees. For decades, cities around the world have been built to keep water off the streets as quickly as possible. Concrete, asphalt, paved sidewalks, parking lots. These hard surfaces are excellent for transportation, but they create one critical problem. They don't absorb water. Instead, every drop of rain is forced to race across the surface, overwhelming drains and rivers within minutes. In Accra, where rapid urbanization has replaced much of the city's natural landscape with concrete, the effect is magnified every rainy season. But what if the streets themselves became part of the solution? Across the world, engineers are embracing a new philosophy known as the sponge city approach. Instead of treating rainwater as a threat to be removed, immediately. Cities are redesigned to capture, absorb, store, and slowly release it. At the heart of this approach is permeable pavements. Unlike traditional asphalt, these specially engineered surfaces contain tiny interconnected spaces that allow rainwater to pass through instead of running across the top. Beneath the pavement lies a carefully designed layer of crushed stone and engineered soil that temporarily stores water before allowing it to slowly infiltrate the ground or drain into underground collection systems. The result is a street that doesn't simply carry traffic, it helps manage storm. Imagine thousands of square meters of roads, parking areas, walkways, and public spaces quietly absorbing rainfall during a storm. Every liter that soaks into the ground is one less liter rushing into an already overloaded drainage system. Instead of forcing drains to handle the entire storm at once, permeable surfaces spread the burden naturally across the landscape. This reduces peak runoff, lowers the risk of flash flooding, and gives existing drainage infrastructure more time to perform effectively. The benefits extend far beyond flood control. As rainwater filters through the layers beneath permeable pavement, many pollutants, including oil residues, sediment, and heavy metals washed from road surfaces, can be trapped before reaching rivers and streams. This natural filtration improves water quality while reducing environmental contamination. At the same time, faster drainage from roads surfaces means less standing water. That improves road safety, reduces hydroplaning risk, and allows emergency services and commuters to move more safely during storm. The future of flood management is no longer just about building bigger drains. It is about designing cities that work with nature instead of against it. Imagine schools surrounded by rain gardens, parking lots that quietly absorb storms, roads that help drain themselves, public parks that temporarily store water before returning to everyday use. These are no longer futuristic concepts. They are already transforming cities around the world. The question is whether Accra is ready to make the same transition. From a city built to repel water to one designed to live with it. Building stronger drains is only part of the solution. The cities leading the world in flood resilience don't just build smarter infrastructure. They build infrastructure that can think. Imagine a virtual copy of Accra, an exact digital replica of its roads, rivers, drains, bridges, terrain, and underground stormwater. Engineers call this a digital twin. Far more than a 3D model, it is a living simulation that receives continuous information from sensors, weather systems, and water level monitors across the city. Every rainfall event can be tested in the virtual world before it unfolds in reality. As storm clouds gather, the digital twin begins running thousands of simulations. It predicts where runoff will concentrate, which drainage channel will reach capacity first, which neighborhoods faces the highest flood risk. Instead of waiting for roads to disappear beneath flood waters, engineers gain valuable time to act before the crisis begins. Preparation replaces reaction. Imagine an underground drainage system that continuously adjusts itself during a storm. Across the network, sensors measure water levels, flow speed, and pressure in real time. If one drainage corridor begins to approach its limit, automated control gates redirect excess water through alternative bypass channels or underground storage reservoirs. Instead of overwhelming a single part of the city, floodwater is distributed across the wider network. Like air traffic controllers guiding aircraft to less congested routes, engineers can manage stormwater where it creates the least risk. Small monitoring devices placed throughout rivers, culverts, retention basins, and drainage channels continuously report changing conditions. Every few seconds, they transmit new data to a central operations center. Engineers can immediately identify which neighborhoods are experiencing the heaviest rainfall, rising river levels, or blocked drainage. This real-time awareness allows emergency teams to respond faster and more effectively, while infrastructure managers adjust the system dynamically as conditions evolve. Perhaps the most powerful advantage comes before the first raindrop even falls. Modern weather forecasting, supported by advanced computer models and machine learning, can provide increasingly accurate short-term rainfall predictions. Using these forecasts, operators could begin preparing the drainage system hours in advance. Underground reservoirs could be partially emptied to create additional storage. Floodgates could be repositioned, pumping stations activated, emergency services strategically deployed. By the time the storm reaches the city, the infrastructure is already prepared. Instead of scrambling to respond, the system is ready to receive the water. Technology alone cannot eliminate flooding, but when combined with modern engineering, strong urban planning, effective maintenance, and responsible land use, digital systems can dramatically improve how cities manage extreme weather. The future of flood protection is no longer defined only by concrete and steel. It is also shaped by information, data, prediction, and the ability to act before disaster strikes. For Accra, that future may begin not with bigger drains, but with smarter decisions. For generations, the rainy season has been viewed as something to endure, a season of anxiety, of traffic gridlock, of flooded homes, of damaged businesses, of lives disrupted. But what if we change the way we think about it? What if instead of treating stormwater as an enemy, we manage it as one of our most valuable natural resources? Imagine an Accra where every major storm becomes an opportunity rather than a disaster. Rainwater collected in underground reservoirs could later be used to irrigate public parks, maintain urban greenery, support street cleaning, or even supplement selected non-drinking water systems after appropriate treatment. The same water that once threatened homes could help cool the city, nourish green spaces, and reduce pressure on freshwater supplies during the dry season. In this future, rainfall is no longer wasted. It is managed, stored, and put to work. Every year, flooding silently imposes an enormous cost on Accra. Roads require repeated repairs. Businesses lose trading hours. Families mourn their beloved, replaces damaged furniture and appliances. Public funds are diverted towards emergency response instead of long-term development. Economists often describe this recurring losses as an invisible flood tax, a burden paid not through legislation but through damaged infrastructure, interrupted commerce, and reduced productivity. By investing in resilient infrastructure today, Ghana has the opportunity to reduce these recurring losses over time, strengthen investor confidence, and build a more reliable urban economy. Flood protection is not simply an engineering project, it is an economic strategy. The cities admired for their resilience did not eliminate flooding overnight. They invested consistently. They planned decades ahead. They embraced innovation, and they accepted that climate resilience is not an expense. It is an investment in the future. Accra can make that same choice, not by copying another city, but by developing solutions that reflect Ghana's unique geography, climate, and growing urban population. The knowledge already exists. The technology exists. The question is whether the vision and commitment will follow. Imagine a rainy season where schools remain open, businesses continue operating, emergency sirens remain silent, families watch the rain from their windows without fear, not because the storm has become weaker, but because the city has become stronger. This is the true measure of resilience, not stopping the rain, but ensuring that when it rains, the city is ready. The future of Accra will not be determined by the next storm. It will be determined by the decisions made long before the clouds gather. Engineering has already shown what is possible. Now, the challenge is transforming possibility into reality, because the goal is not simply to survive the rainy season. The goal is to build a capital city where rainfall is no longer remembered for disaster, but respected as a resource. A city prepared, a city resilient, a city ready for the future.